All right, part 2 of 6.5. Just a little bit more complicated problems here. I'm not going to do this example because it's very similar to the other example I did in the last video, but I do want to point out that these spring questions can get a little bit more advanced. So I'm just going to read through this one and talk through this one, but not actually do it. You guys can look through the book on this one if you want. So a spring has a natural length of 1 meter. A force of 24 newtons holds the spring stretched to a total length of 1.8 meters. First, find the force constant K. B, how much work will it take to stretch the spring 2 meters beyond its natural length? And then C, how far will a 45 Newton force stretch the spring? All right, so first things first is they don't actually give you the spring constant, but they do give you this sentence here, which is what we're going to call an initial condition. So what we can do is we can use Hooke's law, that force is equal to Kx, plug in the force, plug in the x. The x for this example would just be 0.8, since it's gone 0.8 units past the natural length here, and that helps you find the k. Once you do have the k, then you can answer part B, how much work will it take to stretch the spring 2 meters beyond its natural length? So this would just be integrating over Hooke's law, where you use the k from part A. So we're going to integrate over kx, and it's going from 0 to 2, since we're going from the natural length to 2 meters beyond the natural length. And then the last part C here, how far will a 45 Newton force stretch the spring? All you have to do there is just plug that back into Hooke's law again to find the x, the distance that it'll stretch it. Okay, so I'm not going to do that one, but if you're confused about it, just look through the book's example here. I want to do one a little bit more complicated because these do get kind of hard. So let's do this question here together, and then there's another one right after this that we'll probably do here in the same video. So example 4, a 5 kilogram bucket is lifted from the ground into the air by pulling in 20 meters of rope at a constant speed. The rope weighs 0.08 kilograms per meter. How much work was spent lifting the bucket and the rope? And it has a little picture over here. So you have a guy on top of a roof lifting a bucket, but not only are we going to take into account the weight of the bucket and the amount of work to move the bucket to the top of the roof, but we also have the rope itself, which has weight to it, so we're going to take that into account as well. So I'm going to move over to OneNote here again so I can write this stuff out. So first I'm going to bring all my constants over. We have a 5 kilogram bucket, is 20 meters that we're trying to move it, and the rope itself weighs 0.08 meters. So I'm also going to split this up into two different sides of the question. We have the bucket. I don't know why I forget that this thing has an eraser. We have the bucket, and then we have the rope, and we're going to have to do those two separately because we have to tackle the question in two different ways. Look, it actually it saw what I was trying to write. I think that's the first time. That's amazing. Okay, so with the bucket, remember the bucket weighed 5 kilograms, and we're trying to move it 20 meters, I think it was, right? 20 meters up to the top of the rope. Yeah. The bucket's weight is not changing, which means that we are not doing variable work for the bucket. We're just doing constant work for the bucket. So to move the bucket to the top of the roof, we're just going to use the regular formula for work. Work is the force times the displacement. We have to be a little bit careful when we are in this metric system because this number that they give us is the mass of the bucket. We have to actually take that a little bit further to find the weight of the bucket, which is going to be the force. So whenever you're given kilograms, to find the force itself, you have to take those kilograms and then multiply that by the 9.8 gravity constant to get the weight of the bucket, or the force that the bucket is applying for the person. So we're going to take that 5, multiply it by the 9.8 for the force, and then the distance that we are moving it is 20. So we just multiply these numbers together here in a calculator, which I actually grabbed at this time. And we get 980. Because we're in the metric system here, this is 980 joules, but that's just to move the bucket to the top of the roof. That's not taking into account the rope yet. So the rope we're going to have to do separately. For the rope, it gives us the density of the rope, which is 0.08 kilograms per meter. So that was just given to us in the question. And then the rope itself, we are also lifting 20 meters of the rope up. But it's not 20 meters of rope the entire time. As we pull on the rope, it actually gets less and less and less. So we have to take that into consideration. Before we find the work, we have to find the force of the rope as a variable function. We're going to let x here be the amount of rope that we have pulled in so far. If that's the case, to find the force, it's going to be the weight of the rope, which is 0.08 times 9.8 per meter, times the amount of meters that are left over. So we're going to take that 0.08, we're going to multiply that by 9.8, and then we're going to multiply that by the amount of rope that's left over after we've pulled in x, which is going to be 20 minus x. Okay, so this 0.08 times 9.8, that's going to be kind of the weight of rope per meter. That times the amount of meters that's left over, which is 20 minus x. So 0.08 times 9.8, let me just figure out what that is real quick. 0.784, and we're going to multiply that 0.784 and distribute it onto these two things. So now my force, that number here times 20 is 15.68 minus that number 0.784 times the x. And then remember, to find the total work, we're just going to integrate over that. So we're integrating from 0 to 20, since that's how much of the rope that we're pulling in. And we're going to be integrating over this 15.68 minus 0.784x dx. All right, pretty easy integral to do. That 15.68, we're just going to add an x onto that. This one, we're going to square the x and then divide by 2. Which is 0.392. And then we're evaluating that on the limits from 0 to 20. So let me just plug in the 20 real quick and see what we get there. I got 156.8. And again, this is in joules. So this is the amount of work to pull up that 20 meters of rope, which means that the total work would just be adding these two things together. So taking the work it takes to lift the bucket, 980, plus the work it takes to lift the amount of rope that we have, and then just adding those two things together, we get the total work here, 1,136.8 joules. Just to double check, make sure we got the right answer here in the book. Yeah, 1,136.8 joules. Yay! Okay, so we're also going to do this other question here, but I think I'm going to save this other question for the next video because it's going to take quite a while. It's a pretty hard one. So next video, we're going to do the conical